matter.
If I sit down, you see my head. You see my head?
Yeah.
Yeah.
It's right in there. No, not as much. If you lean to the right, you will though.
Do you want to be? Are you camera shy?
No.
All right, so it's 6:31, so we'll go ahead and get started. If you haven't picked up a handout yet, it's the same one I posted on Piazza. At the top, it does say Recitation 5. That's because I got confused after I noticed it after I printed it. But it is, in fact, Recitation 7. There are 2 pages, front and back. My plans for today, so a lot of this you went over in lecture yesterday. So the beginning part is meant to be just sort of a refresher, and then we'll do some practice problems where you can put these concepts into action. So to get started, so yesterday you learned about the concept of, yeah?
I'm sorry, this is something different, but can we, like, at some point quickly go over or take a gradient of X transpose QX?
X transpose Q, yeah.
Okay.
Okay, so we can do that at the end, maybe.
Okay.
So that's not really relevant for what we're doing here, but then if there's time left over, we can go over that together, or we can stay late and talk about it. So yesterday you learned about the concept of duality, which is if you have some sort of constrained optimization problem, you can introduce these new dual variables, u and v, and then you define the Lagrangian, which takes the original function plus these new components that have to do with your constraints, whether they were the inequality constraints here with these u's. Because these were the inequality constraints, that's why u has to be greater than 0. And also the equality constraints. So because of the way we defined u and the fact that here these h's are inequalities, you know that the Lagrangian is always going to be a lower bound on your function value, just because here these u's are positive, these h's are negative, so this whole quantity is going to be negative, and then this is going to be less than your function value. Again, as long as you're satisfying your constraints. So because of this property, we know that if you take the minimum of the Lagrangian, that's always going to be a lower bound to your optimal f star for your primal optimization problem. So here, this gives rise to what's called the Lagrangian dual, where you want to maximize the Lagrangian g of your dual variables u and v, subject to this constraint that u, the Lagrange multipliers for your inequality constraints, has to be greater than or equal to 0. So 2 main things that come out of this. The primal optimal value is always going to be greater than or equal to the dual optimal value, just because the Lagrangian never exceeds the primal function. So that's this property that we pointed out here. That's called weak duality. We'll touch on strong duality in a moment. And importantly, the dual problem is always convex, even if the primal isn't. So we don't go, I'm not going to go through any examples tonight on like where the primal isn't convex, but if you're interested, you can look online for those. There's a list of resources at the end that have some examples. Yeah, so we mentioned that weak duality always holds. That's that the primal solution is greater than or equal to the dual solution, but in some cases they're exactly equal. That's called strong duality. And one thing you can check to confirm strong duality is what's called Slater's condition, which is if the primal is a convex problem and there's a strictly feasible solution, then f star equals g star. And strictly feasible means that when you're looking at your constraints, when you have those inequality constraints, that means you're never on the boundary of those. So like if it's saying x is less than or equal to 0, it's always going to be x is less than 0. So you're never on the boundary there. That's what it means to be strictly feasible. And then just briefly the KKT conditions. There's stationarity, the fact that the gradient of at the optimum value of your gradient of the Lagrangian is 0. Here what's called complementary slackness, that's really going to come into play with support vector machines. And that's that your dual variable u, this is the one that was associated with the inequality constraint, times the inequality constraint itself, those are equal to 0. So this can come up either your dual variable ui is 0 or your inequality constraint here is 0, meaning it's on the boundary. So either of them, at least one of them has to be 0 in order for this to hold. And then obviously you have to satisfy your constraints on your primal solution and on your dual, or your primal problem and your dual problem. So there are a couple of different ways you can go back and forth between the two, depending on if you have strong duality or not. So all of that should have been review. So now I've prepared a few examples that we could go through. So maybe, well, let me know how you feel. But I was thinking I could give you all some time to work on them, and then we can discuss them together. Maybe if someone wants to come up on the board and do them in front of everyone, you can. If there are no fearless volunteers, then I can go through and do them. But hopefully someone will volunteer. And we can just go problem by problem. So here, the first problem is just to give you practice with taking a dual of a linear program. So in lecture, you learned, so a linear program, you have this linear objective function, C transpose X, and then you have these linear constraints on X also. So you have your equality constraint, A, X equals B, and some inequality constraint, Gx less than or equal to H. And then just the formula for the dual, if you go through and derive it, you'll get it, but in this case it's just easier to use the formula. You get this maximization objective instead. So now, I'm going to ask you, what is the dual of the dual? So before we start, does anyone have any intuition about what the dual of the dual might be? It can just be a guess. The primal? Yeah, so in this case it is. You can go through and check to confirm. But this is to give you practice taking a dual here, and you will in fact get the primal. So I'll give you a few minutes. If someone is finished and wants to raise their hand, that'd be cool. How's it coming? Are people still working? Raise your hand if you're still working. Raise your hand if you're finished. Okay. So those of you that are still working, like, do you know where you're going, or are you trying to figure out what to do next? That wasn't a yes or no question. Yeah?
It's really confusing following the variables.
Oh, okay. Okay. So do people want a little bit more time to work on it on your own, or do you want to go over it together now? Like, I don't, if you know what you're doing and stuff, then, and you want to, that's fine. But I don't want you to, like, waste your time being confused. Preferences?
Yeah, what's that?
Yeah, yeah. So, well, first, does anyone, well, no one finished, right? But does anyone want to start off on where you don't have to do the whole thing? Yeah, you go ahead.
Just group D and B one vector and express this into a matrix multiplication.
Yeah, yeah, that's the idea.
But then like calculation 7, that might look.
So yeah, that's the basic idea. If people are confused, I can go through and do it. Like, yeah, when I went through and did it, you can see there are lots of scribbles when I made mistakes. So yeah, I can go through and take you through it. So yeah, like he mentioned, we're going to just define this new variable, which I called x tilde to be the concatenation of u and v. And so this is, of course, an m plus r dimensional vector. So a few other things we're going to concatenate together. We're going to let this c tilde be b and h. So that means it's also an m plus r dimensional vector. Then a tilde is going to be negative a transpose b transpose. So this is an n by m plus r matrix. C tilde, the main thing we need to get out of this is just to enforce that v is greater than or equal to 0. So that's going to be zeros, negative identity. So then, oh wait, actually we need one more. We'll find b tilde just to be c. That's an RN. So you can see now, if we make these definitions, we can then express this dual. If we switch, you notice that if you maximize the negative of a function, that's equivalent to minimizing that function. So we'll take the negative of the objective, which then becomes c tilde transpose x tilde, and then our constraints are a tilde x tilde equal b tilde and g tilde x tilde less than or equal to, here it's just 0 because it's v had to be greater than or equal to 0, so because here we have this negative identity, we can put it on the other side of the equality. So this 0 is, we're going to continue using the full notation, that would be h tilde. So now, if we were to put this in the same form as the primal there, so if we were going to just follow the rules of how to take the dual for a linear program, it would become Oh, and so let's see. Yeah, I'm going to use u bar and v bar for our new dual variables. So v max, v tilde u bar minus h tilde v bar, subject to a tilde transpose u bar minus t tilde transpose u bar. That's equal or c tilde, yes, c tilde. And then we have the constraint that the variable dealing with the inequality constraints, which here is v bar, has to be non-negative. So we can do some simplification already. We know that h tilde is 0, so that means that this part here drops out. Then if we were to go through and expand or rewrite our equality constraint here, we could, if we go back and substitute the definitions of these variables that we defined earlier, we would get that this part equals so here these are going back to the variables that appeared in our primal. Yeah, so then we can just match the top part of each vector with the other side here. So we get that a times u bar plus here it's a 0 equals b, g times u bar minus v bar equals h. And so that ends up, oh yeah, and h was 0. So if we combine these things,
Should g tilde be equal?
huh? What do you, no, so we want this to go with the v part, which is the second half of it. So that's what were you asking? Is this what you were asking, like where the I should be in G? No, so we want it to go with the V bar part of it, which we said was the lower half. Or not half necessarily, but the lower portion. So that's why it comes second.
Okay.
Right, so then if we take this equality and kind of split it up into two, we know we have a u bar equals b, and then g u bar plus, or sorry, minus v bar equals h, and h was 0. Oh no, sorry, h bar was 0. H is h. So because we have this constraint that v bar has to be greater than or equal to 0, that means here that this part is greater than or equal to 0. So this part is equivalent to GU bar is less than or equal to H, because we're subtracting a non-negative number from GU bar. So then you can see the constraints we have. We've changed our optimization variable. What was X in the first part is now U bar, because it was our dual variable, but it's equivalent. So we have, we're minimizing this C transpose, or sorry, minimizing B tilde U, subject to these constraints, where here is equivalent to AX equals B, and then GX is greater, or sorry, less than or equal to H, which was the same conditions we had in the original primal. So it's not always the case that the dual of the dual is the primal, but in this case it is. So this was the kind of the most tedious of the calculations for the problems today, so done with that now. Then this next question, we're looking for the optimal solution for this constrained quadratic program. So I guess before I unleash you on it, does someone just want to say what the first step would be here to solving this problem? Or you can just start working without saying if you want, but I don't want people to not be sure and then end up doing nothing. Does everyone know how to proceed with this one? Or do you want to debrief with it ahead of time? All right, most people are just working, so continue.
So when you do this, what should the majority be?
Okay, so do you want to go through and do that part together so you confirm that you're on the right track?
What the Lagrangian is?
Yeah. So remember that. Well, first, has anyone have the Lagrangian that you want to do on the board? It doesn't have to be right. We can talk about it. Okay, whatever. All right. So if you recall, the definition of the Lagrangian is basically just your function plus these Lagrange multipliers u and v. You introduce one for each constraint that you have in your problem. Right? So in this example, there's only the equality constraint. So that's just the L's. So you're only going to have this part of your Lagrangian. So it's going to be your function plus your Lagrange multipliers times each constraint that you have. Like, is that good? Are you ready to go on? Or
Yeah. It's,
okay, you look hesitant.
so when you take a gradient, it doesn't seem to make sense.
Yeah, it reduces the sign that doesn't seem to be reduced.
Yeah. I think I'm just messing up the gradients.
Oh, okay. So does anyone? Do you want to just like go up and write what your Lagrangian is, and we can talk about it?
Okay.
Okay. Yeah, that's right.
So, yeah, I'm not sure how to proceed with this.
Okay, so then you're going to differentiate your gradient, or sorry, your Lagrangian with respect to x, right?
Yeah.
Okay, and what did you get from that?
Yeah. So, are we differentiating or are we taking the gradient?
Well, so it's with respect to x, right? So there's lots of variables in there, but the only one that you're taking the gradient with respect to, differentiating with respect to, is x. So everything else you can pretend is constant.
Right. So this should be x.
Right?
This should be U transpose A.
Yeah.
That doesn't.
Well,
That's a column vector and that's a row vector.
yeah, so basically what you need to do though is you just like transpose that second part. So it's going to be A transpose U. Yeah.
Right. But why do we do that?
Well, the easy thing to say is because it lines up. But technically, like depending exactly how, so when you're doing all like vector calculus, there are ways, like different ways of defining how to do things exactly. And so you can take your gradients so that they're columns, you can take it so they're rows, and then in the end it just each becomes the transpose of the other. So in this case, it's going to be A transpose U.
Okay, so just to make it match up, we just
Yeah.
transpose that.
Yeah.
So
And so, yeah. And so then, like, because the stationarity, you'll set that to 0,
Yeah.
and then,
And the next will be like negative U transpose U.
Right.
And we plug that into the condition. We can do that, right?
yeah.
Yeah.
So, right, that's here you're using a couple different of the KKT conditions. First was stationarity, just you know that the gradient of Lagrange was 0, and then here you were just going back and ensuring that you were getting a solution that was feasible for your primal here, which your condition is AX equals B. So you just substitute in your value for X into that to find exactly what your dual variable U needs to be.
A transpose inverse B.
Yeah, that's right. Did everyone else get that? Does anyone want to talk about it? Okay, let's move on. So there was another part to this question. So assume that you choose A and B in your constraints such that a feasible solution does exist. So in this case, what is the duality gap? What's the difference between the optimal value of the primal and the optimal value of the dual?
0.
Right, and why is it 0?
If you plug it in, you get 0. But I don't know why.
Oh, were you just comparing your?
So like
Did you do the dual?
So if we just plug in the optimal value of x right there, that offset becomes 0. Right? Like U transpose times AX minus B becomes 0.
Well, that would always be the case as long as it's feasible. So here we're really asking if there's no duality gap, that means there's strong duality. And what's the thing that you learn to check for strong duality? Couple pages up.
They're both equal, all three equal.
Primal is convex.
Right. So we assume that you chose A and B, so there would be a strictly feasible solution. And the primal here, it's just a quadratic program, which is convex here. So we know that strong duality holds, and the primal solution is exactly equal to the dual solution. Okay, and then here we have another linear program. Here I just gave you the primal and the dual. We can go through these few different examples, and you can say whether or not they would be solutions, valid solutions for this problem. So the first one, here x star equals 0, that's just, so here x is a 3-dimensional vector, so that just means every entry is 0. I didn't write it out, that was lazy. So would x star equals 0 be a valid solution for this problem?
No.
Okay, no, why not?
Satisfy the conditions.
Right, so it doesn't satisfy, like in particular, this second condition that x2 minus x3 has to be less than or equal to -2. And so that was one of the KKT conditions, right, that primal feasibility had to hold. What about this next one, v star equals 0? Could that possibly be a solution to the dual? Okay, more head shakes. Why is that? Yeah, so it violates here the dual conditions, which dual feasibility was another of the KKT conditions. Here, what about x star equals 1, -2, 1? Could that be a potential solution? See some nods. Let's see. So it does satisfy the conditions, or the constraints on the primal. However, there are a few other things that you would need to check. So for this, like I didn't tell you what the dual solution would be, but just if you were to like, cheat and use the other potential values that I gave you, you would see that something does give a lower value for x1 plus 3x3 than this one does. Right, so say example you took here, this x star. So x1 plus 3x3 is going to give you a value of 2. This x star, x1 plus 3x3 will give you a value of 4. So you know there exists something else that is lower. So this can't be it. Yeah?
But if it's just asking like, could it be a solution, not like, is it the solution, then how do we know that we have to like check for?
So here, the idea was not to have you completely solve it. Of course, if you wanted to know the full solution, you would solve it. Because there's an exact solution for this.
Yeah.
You can just do like a LP solver for it, which is what I did. But here, given the information you have, it was about like looking at things. So this one, yeah, that was kind of like you couldn't verify it directly with the KKT conditions because I didn't tell you what the corresponding dual solution would be. But if you were looking at like ways that you could minimize the value, then you would see that, for example, there is at least one value that gets lower. All right, what about this fourth one? So here I give you both a potential primal solution and a potential dual solution.
Doesn't satisfy the first condition.
For which variable?
The dual condition.
From -1.
Oh, it doesn't. Oh, darn. Okay. Well, I didn't pick a good example there. This one, it was supposed to fail. It also fails at complementary slackness. But okay. In that case, I didn't get something that satisfied all the dual constraints. So that's another way to check there. All right. And then, so what about this last one? Could it be solution?
Also doesn't satisfy the same condition.
Wait.
Oh, nice.
Which one doesn't it satisfy?
That satisfies that.
First condition of
The first condition, 1 plus 5 minus 3. Yeah.
Oh, wait, oh yes, it's the -1.
Oh wait, did I?
Yeah.
Alright, well, the typo I also wrote it up wrong on my paper. But this one, it was supposed to be correct. So, was it not? No, you're right. 1. Okay. Well, somewhere I wrote something down wrong. Sorry about that. I'll fix this and put it back on Blackboard. But the idea for this one was you could also check the complementary slackness conditions, which are for your inequality constraints, the product of the Lagrange multiplier for that constraint and the value of that constraint has to be 0, meaning either the constraint has to be equal to 0 exactly, so it's right on the boundary, or the corresponding Lagrange multiplier needs to be 0. So if you go through and you check all of the conditions here, the only one where the actual value doesn't equal 0 is this first one. So that's the -x1 plus x2. So here that would be -1/2 plus -3/2. So that would be -2, which is not equal to 0. But in that case, the corresponding dual variable is 0. So that's why the complementary slackness holds. And for all the other conditions, they hold exactly. Okay, yeah, so that was all the examples that I had planned for today. At the end, I just have a short list of resources that are kind of comprehensive on this topic. So for the Boyd and Vandenberg, the convex optimization, that's the same one that Barnabas passed around in class the other day, but it's online. I have the URL here, and the duality chapter is chapter 5. So if you want to focus on this, that's the you want to zero in on. And then, yeah, just a course here at CMU on convex optimization that has a lot of information also. So that's it for now. I know someone had a question about taking a particular gradient, so I don't know if people want to stick around for that, but the official recitation is over at this time.
So the first step was wrong. You don't just get to the x. So then what you can
I guess you just plug it back in.
Yeah, it's like action.
Oh yeah, so here, right, you just say your x is review, so you can substitute this back into x to
Yeah.
get x in terms of things you already know, and then you know x.
I get it, it's just
like substituting back.
It's just algebra.
Yeah.
And then I feel like,
It's just like something that you can do with math. And I think like, it's still like, I'm still kind of very loose on matrix differentiation. Huh? Like, in general, like, there's differentiation in math.
So actually it's
I mean, the codings are okay, but like, not all set.
and then that entire product is the inverse.
they're very convenient.
Or wait, what is?
I feel like our like, linear algebra curriculum
Right, so you got this.
is really, really bad. It's only like 241. 241 doesn't teach you anything.
So is there more advanced version?
Yeah, but I don't think 242 talks about like
So here, what do you think that?
differentiation.
I actually like that book that
Yeah, but like I
just have it handy, so
just have it next to it. It feels like a lot of math in this program is
well, then that's a good point.
I don't think I could ever be a PhD.
Well, I suppose the majority of the math and the PhD is not real, it's just abstract. Or
Well,
like,
the thing is,
you just copy, not like copy.
you found x, but in terms of something you also
It's
don't
been
know.
solved.
Right? But you do
I
know
guess
a thing about
maybe if you're math,
what
if
actually
you're
holds
PhD,
of x, you would just string.
I wouldn't want to study.
Get your
I don't want to.
unknown
I wouldn't want to like
B
do research.
in terms of things you know theory.
Yeah, there's like things out people are thinking about stuff.
Thing for x. So you guys are optimizing x, and then if you want to find the exact value, I didn't do that. Oh, their code about like finding things that when you would apply them together would give you the quantities you were looking for, right? So like when I did it, I was like, yeah, that's pretty neat. Like you cram those together and then look at exactly what pieces need to go together. So like obviously I was incorrect. So then I just like double checked to see like to confirm this is how I found out I made mistakes. Well, not really, because right, you should know the way that like, when you're doing like matrix multiplication, what pieces go together. But it's like confusing. Yeah. To go through it. Yeah. So you just have to Yeah, I'm for it. Okay, I will see you then.
Yeah, it's okay.
Yeah.
So how do we define something like gradient of a row vector with respect to column vector? Is this even thing?
So here, when you've been doing gradients, here your answer was a real value. So that's already something different.
Right, yeah. So is this defined? If we're taking the gradient with respect to some factorial thing, instead of a real number factor.
Yeah, so, I don't know off the top of my head, you can look online. But for at least our purposes right now, this is not coming up.
Okay. And so what we did this in here. And he said that it was 2A or something. I think it was, yeah, he said it was, or 2AX, sorry.
Oh, okay, yeah. So if A is symmetric,
If only
then
A
it
is
is,
symmetric, yeah.
right. The, more generally, for this one, it's, it's like A transpose plus A,
Okay, yeah.
all of that times X. So you can just write if it's symmetric, then A transpose equals A, so that's why it's 2A in my case.
Right. And the way to do that would be, if we first say that this is constant, then it would be AX, right? And then if we say that this is constant, then it would be,
Yeah, so basically just the product rule.
right? So it should be this, right?
Yeah.
Yeah, that makes sense. Okay, thank you.
Sure. Okay. Yeah, my office hour is still Friday at 4, in case you want to talk about stuff then.
Which other one? The one that's not supposed to be. There was yeah. It's not. No, it gives you two x, right? Like, the x comes from like half x transpose x.